just about to start.
Yeah.
Right, so before the break, left you with looking at, well, we're about to start looking at multi-homing with multiple customers. And I was talking about ISPs not wanting to do custom configurations for customers. They like to standardize things as much as they can. And so that's really what RFC 2270 came from. The folks at Internet MCI documented how they handled multiple customers who multi-homed onto their backbone. And that was RFC 2270. So it lets them standardize the configuration, making it very simple for them to support lots and lots of customers. So as I say here, it's very unusual for an ISP to have just one dual-homed customer. And it's actually quite a valuable and valid service to give this option to your customers. Now, even though I said in the early slides, well, you want to try and encourage two of everything, go to two upstream providers and all the rest. I suppose this is one way of persuading your customers that, well, you can multi-home onto your backbone into different POPs and so forth. And that's better, well, from a sales point of view, than letting your customer multi-home to another provider, and then they can compare you with them. So this kind of goes against what I said earlier, but it's a useful service to offer in any case. Certainly if you've got multiple POPs in your backbone. We found it very, very valuable in the UK to do this. We would have national customers who connect in London, Manchester, Edinburgh, and so forth. And it was very useful service to offer for them. They could get good redundancy onto our backbone without having to go to two providers. So if you're going to do this, you want to try and look at scaling the configuration. You don't want to do a custom configuration for each customer. So you want to start using templates, BGP peer groups, which is a nice handy shorthand in Cisco iOS. But basically, you're giving every customer the same configuration. Picture looks like this. So AS100 is the operator. C and D are the access routers where the customers are connecting. And then we've got these various customers. No mistake here. AS65534, that's the autonomous system we use for each one. They can all have the same autonomous system, because all they are getting is a default route from you. They're not getting the full BGP table, so we don't have the AS path loop detection taking place. There's no AS path loop detection. They only get the default route. They announce the address block to their upstream provider. So all these folks are seeing are just the default route and their own aggregate, nothing else. Right, so that's the setup. And because it's like this, we can make it really quite straightforward. Customer announcements are as before. We're using the same private AS for each customer. I found that some ISPs who do this use a public AS number. That's up to you. I mean, if you've got AS numbers in your back pocket and you're not using them for anything else, then you may as well use a public AS number for this. It means that your multi-homed customers onto your backbone have a public AS number, and is there a technical advantage? None that I really know of. But they're in a separate AS from yours. But private AS works just fine. Documented in RFC 2270. The address space is not overlapping, so this is not a problem either. Each customer only hears the default route. So all the router A and B configurations are the same as they were before. So here's a router A configuration, same as it was for the load balancing one example earlier. So router C out, here's the aggregate and the sub-prefix as an example. Router B configuration, same as before, the 19 aggregate and the sub-prefix. It gets more interesting for the upstream ISP, because now we can use a BGP peer group. Now, if you know Cisco iOS, you have read the Cisco documentation that says, well, peer group, don't use it anymore. There's not any point. Well, from a performance point of view in the router, it doesn't make any difference. But for a configuration documentation point of view, I still love them. Because what it does is it groups all the common configuration in one place, and then you can apply this common configuration throughout the router config. So that's why I actually quite like how the peer group is set up. I mean, yes, Cisco says you've got peer templates and blah, 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 but I find peer templates, the configuration is very messy compared with the simplicity of the peer group. Obviously, if you've got more sophisticated needs, then these won't work. But this keeps it nice and simple. So in the peer group, we put our AS number, 65534. We put in the default information originate, so we send the default route to the customer. Outbound filter, sending only just the default. And then we apply the peer group to each of the customers like that. Notice we still have the inbound filter. One message over the last few days has been always filter prefixes, inbound, outbound. The presentation from Tata mentioned exactly that, filtering in and out. Peer group, BGP customer. So each customer you add, just simply they join the peer group, get a nice description, and you have the inbound filter from them. So it's very simple. You add the prefix list here, and you're done. So that was router C. Router D configuration is the same. When you get to the upstream edge, strip out the private AS again. So remove private AS, prefix list customers out. So again, our customer prefix filter we just throw in like this. So each new customer we get, we add them to the border router, and they go into the prefix list like this. Okay, so that's pretty simple to do as well. If the customer's prefixes come from the ISP address block, then what we can also do is, when I've conveniently picked the addresses so they all come out of this /13 aggregate, and so we only need to announce the aggregate, because the customer address space, it doesn't add any extra value to the internet at all. Right? The upstream providers only needs to send the aggregate outbound, not the individual pieces. So that shows you how to simplify the configuration for multiple dual-homed customers. Use a private AS, leak sub-prefixes to help with load sharing. Upstream router configuration is identical as it was before. Now we're going to look at multi-homing to different ISPs, and what changes here is we now need to use a public AS number. So if you're a member of RIPE-NCC, you can go to the registry and you can get an AS number for your customer if they need to multi-home. And that's pretty easy. You can do that as part of your membership, as you can with all registries. Some people use a private AS. I mean, if you're multi-homing between two upstream providers, you can use a private AS. BGP doesn't know what's private and what's public. I mean, we have decided what's private and what's public. BGP doesn't know. But the thing is, you then get, appearing on the internet, prefixes that appear as though they're originated from two different ASs. And that's what's known as an inconsistent AS. And you always get somebody trying to be too clever, saying, ooh, this is illegal and shouldn't be happening and all the rest. It's not illegal at all. Two autonomous systems can originate the same address space, because usually between those two ASs, there's another hidden one. There's the private AS hidden, which you cannot see. Right? And so it's like this. 200 and 210 are both upstreams for AS65534. It's multi-homing. You're sitting out on the internet. It looks as though 200 and 210 are originating the same address block. Not illegal. Nothing wrong with doing it. You can find out, show IP BGP inconsistent AS. This is the iOS command that will show you on a full BGP table router all the autonomous systems. Last time I looked, there weren't many. There was only like two or three, not two, it's about 60 or 70 address blocks fell into that category. So it's not really very many at all. But there are cases, and they're usually caused by folks multi-homing like this. Some of them are accidents, but most of them are caused by this type of multi-homing. But, there's so many autonomous systems. It's a 32-bit range. There are 4,000 million, well, 4 billion World population's 8 billion. That means we can give every 2 people one autonomous system number. So we have plenty of them, so there really shouldn't be any limit to who can use an AS number for anything. So don't fear about getting an AS number for any of your multi-homed customers. Now let's look at some examples. Primary, backup link. Here we're going to use the AC link as primary, the BD link as backup. All we're going to do here is announce the aggregate on the AC link, and on the BD link we announce the aggregate with a longer AS path. So we sit out here on the internet, and it literally means that the internet sees AS130 with a long path this way and a short path that way. Shortest AS path wins, so traffic from the internet through to AS130 will take the path through AS100. That assumes that AS100 and 120 don't do anything else. You could get a case where 120 does high local pref, and you may find the primary backup no longer works as you expect. But all things being equal, shortest AS path wins. Traffic from the internet to AS130 will come around this way. If you make a prepend long enough, even traffic from AS120 will run around this way. Because if you say do 4 or 5 prepends here, AS120 will see the best path through 100 and round the other way. That's what we're doing, announcing 19 aggregate on each link. Primary link makes a standard announcement. The backup link does an AS path prepend. We make it look artificially longer. Of course, when one link fails, you announce an aggregate on the other, so you get automatic backup. That's the configuration. The router A, just the standard. Aggregate out here, default in there. That's it, simple. The backup, again, we have aggregate out, default in, but now we have 2 route maps as we had before. The outbound route map, I chose to do 3 times prepend. No real reason. I just thought, well, 3 prepends seem to be a good enough number. So if you go to AS130's upstream, it sees this destination with 4 AS hops. Whereas you see it from the other router, it's just 1 hop. Okay, so this is a longer AS path than the other one. For outbound traffic, we hear the default route coming from the upstream, set local pref 80. This makes it the backup for outbound traffic. Right, so the other one has a default local preference of 100. All right, so that's the 2 links to different ISPs, 1 primary, 1 backup. Would you use this? Well, it's not that common, but you tend to find it being used when the 2 competing ISPs agree to provide mutual backup. That's pretty common, and especially in developing parts of the internet, where international infrastructure is expensive, and you have 2 operators. Rather than both of them buying 2 links, they buy 1 link and then agree a backup, a mutual backup arrangement with the other provider should they have a link failure. And that's how you do it. You announce your address space to the backup provider with a long AS path prepend. And that way, they only get used, their path only gets used if the primary link fails. Right. So it shows the basic concepts of using local pref and the AS path prepend. Let's try it with load sharing. So rather than using primary backup, we want to have some traffic on this link, some traffic on that link. Again, we announce aggregates. So aggregate out this way, aggregate out that way. That gives us backup in case either link fails. And then we also take the aggregate, divide into 2 pieces. We send the first 20 out this way, the second 20 out that way. So as far as the world is concerned, traffic for the first 20 will come in here. Traffic for the second 20 will come in there. Okay, it's a bit of a, I suppose a bit of a shot in the dark, really, to try and work out what's going to be right. But as we did with the previous examples, let's start with a /20, see what happens. You may have to fix addressing. You may have to divide down into 21s. Who knows? But you start with this and see what you get. Keep it nice and simple like this. When one link fails, aggregate announcement means you get the backup. The configuration looks like this. First address block. So the first address block is the 19 aggregate and 1/20 we send out. And router B is the other address block aggregate and the second /20. So it's a very simple approach to trying to do it. I'm not saying this is the ideal way to do it, but it shows you the principle of subdividing address space to attract traffic in. Notice one thing I didn't mention. If we go back to the picture, it even means that if AS120 is sending traffic to the first /20, it'll go all the way around this way. And that may not be optimal, and we'll cover that a bit later on in the slide set. It may not be optimal doing that. But it's a first cut at trying to at least load balance on your inbound links. Okay, more controlled. Let's try with a bit more sophistication. So again, we want to try and load balance the links. We send the aggregate out this way, default route in here, aggregate out that way, default in, but also announce one sub-prefix. This is a lot more common, because now you've got two things you can adjust. We're announcing the aggregate out this way with an AS path prepend. So you can adjust the length of the AS path prepend as well. The longer the prepend, the less traffic. Right? Because the longer the prepend, the more of the internet is going to use this as the incoming. The shorter the prepend, the more will come this way. Leaking a sub-prefix, well, you leak a /20, in theory, half the traffic will come in there. But if you find it's too much, well, you can make the AS path slightly longer, or you can make the prefix slightly smaller. So you now can adjust the AS path prepend as well as the sub-prefix being sent out. So you've got two variables you can adjust. This is a lot more common. People use defaults on one link, so they aggregate in the default route, and on the other link, they vary the prepend and they vary the sub-prefix size that they leak. They may find that 120 doesn't work. They may need to send 221s or something. But that's the sort of principle that folks follow. So that's what I said. Configuration, router A, very easy. Default in, aggregate out. Done that before. Router B configuration, default in. Outbound, we're sending the 19 and one of the /20s. We've got a route map as well. If we send the aggregate, we're doing it twice prepend. And so we put our AS number in there. We could do a single prepend, double, triple, whatever. The longer the prepend, the less traffic comes from the network. The shorter the prepend, the more. We can change from a /20, we can make it a 21, or two 21s, or 22, whatever. Right? So these are the things that you can adjust. And generally, if you're trying to do load balancing in two links, this is the most common way that people are trying to do it. It still doesn't explain the 22 times prepend that I see in my routing table report, because the internet's not that deep. The internet average is about 5 ASs deep. And like the longest AS pass I've seen is probably 8 or 9, really. So how a 22 is going to help, I'm not really quite clear. Right, so this is more commonplace. The main thing is to make sure that the 19 aggregate is always announced. Now, so those were the simple examples. We haven't done anything about outbound traffic flow. We've only worried about inbound traffic flow. We also haven't done anything about, well, what if one upstream provider is in Europe and other upstream providers in Asia? We don't really want traffic going out into Europe and the response coming back through Asia. Packets going around the world have got big round trip times. It means customers complain. So we want to look at trying doing this a bit better. So I'm going to step up a gear. We're going to look at a little bit more complicated examples. So previous ones dealt with load sharing inbound traffic. Now we're going to look at outbound to balance link utilization and also to try and keep most traffic flows symmetric. Right? That's what we're also going to try and do as well. If your upstream providers in the same location, you don't need to worry too much about this. But if you're deciding to do Asia one way, Europe, North America the other way, you really do want it to be symmetric. I mean, I see this especially as an issue in South Asia, where after the Taiwanese earthquake, so many operators are now splitting between the Asia-Pacific route and going through the Middle East, Mediterranean, and so forth. So, and there they do want it. They don't want to go to, for example, the BBC website in London and have the responses coming back round through Los Angeles. Okay, so balancing outbound traffic requires inbound routing information, where the common solution is, oh yes, you need the full routing table. Please make sure you have these models of routers. And if you don't have these models of routers, we're very happy to sell you them, or loan or rent you them. I see that renting happening quite a lot now. Oh yeah, we'll rent you a big Cisco or a big Juniper router so you can multi-home. It's like, why? Right? It's very rare if you're at the edge of the internet that you need the full BGP table. If you're a transit provider, you do generally need the full BGP table because your end users want to do what I'm talking about here. But I don't know, I've been involved over the years, dealing with small Pacific islands, little ISPs in Africa, and little ISPs in South Asia and Central Asia, who's like, yeah, my upstream is saying I need to buy this Cisco or this Juniper, and it costs $120,000, and I've only spent $6,000 on my whole network. I can't afford this, but I need to multi-home. Philip, can you help? So I've done things like gone into my lab and started up my Cisco 7200 and done show version and said, right, take this show version, send it to the upstream provider, because I've got 2 gig of RAM, for example. And the upstream goes, oh yeah, that's fine, that's great. And then they can use the tiny little router with no memory to do the multi-homing. Right, full routing table is rarely necessary to do load balancing. As I'll show you in a few slides, it's actually a serious hindrance to trying to doing it properly. Right, common myth, you need the full table to multi-home. Not really. You need the full table to carry a lot of prefixes if you're a transit provider, but if you're at the edge of the network, not really. It can actually be a serious hindrance, as I'll show you. You need a big router to multi-home, while router size is all about packets per second. BGP is not about packets per second at all. BGP is about reachability information. I mean, full BGP table. When you buy a mobile phone, does your mobile carrier give you every single telephone number in the world? They don't. You only have the ones that you need. Your friends, your colleagues, and all the rest. The rest of them, you don't care. You can ask somebody, phone up directory inquiries, and they'll tell you, oh yeah, this is the number for such and such. And so it should be with BGP as well. There are parts of the world here where you've got where customers or viewers will have no interest in whatsoever. So why carry those routes if they're not giving you any useful information? In fact, all you need to multi-home is have 2 interfaces able to talk BGP to 2 peers, be able to handle BGP attributes, and handle at least 1 prefix, your own. And the third one I love, BGP is complex. BGP is not difficult. BGP is actually really simple. In wrong hands, yes, it can be complicated, but keep it simple. Start with something really simple. Well, I'm sure all of you have family, you've all have children. You didn't teach your child to walk by entering them into the local athletic club race. No, they learn to crawl first and then start pulling your house apart as they started clambering over things. And then they learn to walk. So it should be with learning BGP as well. Don't look at like a tier 1 configuration that's 20 pages long and go, oh my gosh, BGP is so complicated. It's actually not. Start with some very, very simple things. Strategies. Take the prefixes you need to aid traffic engineering. That's so important. Look at NetFlow data for popular sites. Right? The NetFlow data tells you what your customers are doing. If you're not running NetFlow, JFlow, SFlow, whatever your flow is, you have no clue of what's going on. Absolutely no clue at all. And again, when people come to help me and ask for help with multi-homing, load balancing, the first thing I ask is, okay, what does NetFlow say? What's NetFlow? It's like, well, don't you know what's running in your network? You need to turn on NetFlow. Even if it's sampled on the bigger routers, it still gives you a good idea of what your customers are actually doing. And I think it was mentioned yesterday, there was a NetFlow AS aggregation thing. Use a tool like that. It tells you the most popular ASs that your customers are actually grabbing traffic from. And if you find that it's Google or Akamai and whatever the big news media that your customers use, well, those are the people you really need to worry about and where they connect and how you connect to them. If they're 5 AS hops away, you need to get a better transit provider. If they're at an exchange point, you need to go to that exchange point that they're at, because it'll be a lot cheaper than paying for the traffic. Right, prefixes originated by your immediate neighbors and theirs will do more to aid your load balancing than prefixes that are many hops away. So concentrate on local destinations. By local, I mean connected to your upstream and their upstreams. I don't mean physically local. I mean local as far as the internet's concerned. And try and use defaults as much as we can, and I'll show you. So, we're going to look at these examples. I might skip over this one if we run out of time, but let's see. We're going to look at one upstream, one local peer, one upstream, an exchange point, two upstreams, one local peer, three upstreams, unequal bandwidth. This will show you why having lots of upstreams is really a nightmare to try and handle. I mean, three upstreams in this case, and this is a real live example that actually had to work a few years ago. And it's still current-ish today. It's a bit of a mess. So you really want to avoid having too many upstreams because it makes it very complicated. Right, one upstream, one local peer, very common. Connect to the upstream to see the internet, connect to the local competition so that local traffic stays local. Don't show it to your salespeople. They don't like connecting to the competition because then the competition will steal all your customers. Of course, your salespeople forget that they can steal all the competition's customers, so life stays normal just as it was. Only your customers end up being happy because there's no latency. And you end up being happy because, well, you actually have more capacity available for international traffic. It doesn't really save money, but you don't spend money on transit costs for local traffic. This is the picture, very simple. You're here, router C goes to your upstream, router A goes to a local peer. Notice they are separate. They're separate routers. Yes, you can run them on the same router, but I don't like doing that. And I don't like doing that because of the hijack issue. If you run these on the same routers, this router here should only carry prefixes that you want your local peer to see, nothing else. If you put a default route to the full BGP table here, they could point a default route to you and whoosh, use you for outbound traffic. Now, yes, I know you can put packet filters in to stop all that, but then packet filters take up CPU and everything else on the router. It's much easier just not to give them any destinations. Put a default route to null on here, just carry the prefixes you want these guys to see. If they point a default route to you, this router drops all the traffic with no destination straight on the floor, very easily, very cheaply. So, you know, I was discussing with the folks doing the security workshop last week, and they're talking about, oh yeah, we could set up VRFs for this and that. I'm like, why? All you have is a null route on here. Just make sure this router only carries the local prefixes, nothing else. Much, much easier than doing umpteen different VRFs and black hole triggers and, you know, auto-configuring whatever it was. I don't know what it was. I didn't understand it. Because all I've ever done on all my career is this router only carries local prefixes and a static route to null for the default. And that's very simple. So there we go. Outbound to the upstream, you aggregate inbound default route, and the local router, the local peer, just gets local prefixes. So here's our router A configuration. We send our aggregate there, outbound to our local peer. Inbound, we accept the prefixes they say they're going to send. They're going to send us these two aggregates, so that's why I'm going to accept inbound. And that's it. That's all we need on the router A configuration. Very, very straightforward. Some ISPs use this. Rather than doing an inbound prefix filter, they use an AS path filter instead. And this says, allow any prefixes originated by the neighbor. Technically, there's nothing wrong with this. The danger is that AS120 can originate any old rubbish, and you'll accept it. And you may not want that. Right, we've had many accidents over the years in the internet where somebody has accidentally originated prefixes. And because they've only been an AS path filter, they originate the prefix from their AS, it gets into another provider's backbone and leaks out into the internet. You know, we've heard various things, you know, YouTube incident in Pakistan, we've had the AS7447 and the Florida IX thing and so forth. You know, these are all well-publicized examples. So AS path filter is very trusting. If you know your neighbor really, really well, know he'll never ever make a mistake, then you can probably do this. But it's actually much safer to do the prefix filter as I have here. It's higher maintenance because when they add another announcement to the BGP, you've got to update your filter to let it in. But really, this is the best way of configuring BGP, to have inbound and outbound prefix filters. Okay, router C configuration. This is towards the upstream, so we just have default route in, aggregate, outbound like that. Very simple. Right. So as I've said here, two configurations possible for A. Filter list assumes the peers know what they're doing. Prefix list, higher maintenance. Some ISPs use both, so both have a prefix filter and an AS path filter. Their argument is that, oh, well, but if they announce their aggregate, but it comes from another AS somehow, then we block it. It's like, well, okay, that's, really looking for a bad case. Knowing that the prefixes come from the neighboring AS, we just allow it in anyway. Okay, so private peers, the peering ISPs exchange prefixes that originate. Sometimes they exchange prefixes from neighboring ASs as well. But just make sure that they only carry prefixes you want your peer to see on your peering router. It's a peering router. It's not doing transit and backbone and core and access as well. If you're going to peer with anybody, dedicate a router to it. I mean, that's pretty much best practice these days. Routers are cheap compared with the damage that could be done to your backbone or your customer base if something goes badly wrong. Right? I've suffered from this, of carrying a full BGP table and a default route on a peering router, and only discovered the bandwidth being stolen or bandwidth being hijacked simply by looking at the NetFlow records. And if you're not running NetFlow, you have absolutely no idea if this is going on or not. Yes, you can use packet filters, but bear in mind, packet filters on whatever platform take CPU, whether it's line card CPU or control plane CPU, depending on the platform. The exchange point example is very similar. It just scales it, right? So again, very common. You've got one upstream transit provider. You connect to the local exchange point to peer with all the local ISPs. And so the picture looks like this. You're here, your transit provider 130, your router A now connects to the IX. You've got the Ethernet switch here. Other people bring the routers. Your router sits at the IX as well, and you peer eBGP with everybody there. Right, so we do the same as before. We announce the 19 aggregate. We accept the default route only from the upstream, accept all routes originated by the exchange point peers. Configuration, we can scale it again. Right, so router A, here we address on the exchange point LAN. I've made it a 26 for no good reason other than example. We can set up a peer group, because our outbound announcements to all the exchange point peers are exactly the same. We have an open peering policy, so we send our address block out. Best practice, strip out private AS. I'm going to send a community. I have no idea why really, I just put it in. We're also going to set the local preference for all the prefixes we learn from the exchange peers high. I do that deliberately. I want to send local traffic over the exchange, unless the exchange is not working. And then I'll fall back to the upstream. Traffic over the exchange is free. Going through my upstream, I have to pay for. So I set it high local preference, even though at the point here, I'm only getting a default route from the upstream provider. There may be a time in the future I get full BGP table from the upstream. And then, I've run into issues over the years where this has not been set and the best path has been through the upstream provider and not across the exchange. Okay, so here we go, remote AS, and we apply the peer group to each of the neighbors. And each neighbor we add, we just apply the peer group. So it's quite straightforward. Then we've got the filters from each peer. Again, if you're on the exchange point mailing list, each provider will send an email saying, hey, I've got this new address space, please update your filters. So you just add it into the prefix list, do the route refresh, life's good. Notice one thing, router A doesn't generate the aggregate. The exchange point router is at the physical exchange, is not part of your backbone, physically. It's somewhere else. It has a single connection back to your backbone. If that link broke and you're originating your address block at the exchange, outbound traffic will go through your upstream. The return path would be to your exchange point router for the local peers. So that router has no path back to your network. It would drop all the traffic in the null interface. So make sure, notice the router A configuration, no network statement, no static route to null for your address block. It's done in the core, not in the edge. As I was mentioning on Sunday in the keynote, make sure you only originate the aggregate in the core of your network, not at the peering edge or the upstream edge. Otherwise, you cut yourself off if a link goes down and you spend many, many minutes and hours trying to get people to switch your routers off or unplug them or whatever else. Router C towards the upstream, same as before, default in, address block out. Boring, really. Router A configuration, prefix list, higher maintenance but safer. Don't generate the aggregate. Exchange point traffic goes to and from the local exchange. Everything else goes via the upstream. If the exchange point connection breaks, then your upstream provides you with the backup. So this all works fine. And as I said before, make sure the exchange point border router only carries the prefixes you want the exchange point peers to receive and the destinations you want them to be able to reach. Right, so make sure that. Otherwise, they could point a default route to you and unintentionally transit your backbone. The IXP routers at an IX and distant from your backbone don't originate your address block there. Now let's move over to two upstreams, one local peer. Local peer is not really relevant. The configuration is as before. But having one upstream provider, as we saw earlier, no redundancy. So let's try and add some redundancy into this. So we add in a router D going to an AS140. How do we do the load balancing here? Well, and we've done it earlier before the coffee break. You know, we said, just get two default routes from the upstream provider and we can chop address space and so forth. But that was the easy one. We want to do this slightly better. So yes, we can accept the default route notice that router C and router D are separate. I have the two links, so if this router breaks, we still have a connection. If we only had one router there connecting to the two upstreams, router breaks, everything goes. So separate router C and D. And this is, not very useful. Default in, aggregate out. Default in, aggregate out on router D. We saw this earlier, and we decided it wasn't really very good. So we need to try and do more. And we saw the examples of how to deal with load balancing inbound traffic. But how do we deal with outbound traffic? Because defaults, nearest exit, cheap routers, for sure. They don't need to be very big. But if you've got international links that are going to different parts of the globe, you want to be able to do proper load balancing and not this nearest exit thing. So there are two ways. You can accept full routing from both upstreams. Sure, 460,000 prefixes, excellent. End up with 920,000 paths, lovely. Your router vendor suppliers will be delighted because you're buying all this expensive memory. There's actually another way you can do it, and that's the default route from one upstream and some routes from the other one. And this is, I've converted so many ISPs with the edge of the network from doing this to doing that. Usually because they've run out of CPU or run out of memory in the routers. Or the customers get so annoyed about the long time it takes to converge if one link fails. I mean, 460,000 prefixes on a smaller router takes quite a long time to strip out of the BGP table and the fib. So, and this, of course, when you're going through this convergence phase, it takes quite some time to do it. So, okay, we know how to load balance inbound traffic. We did that earlier. How do we load balance outbound traffic? Well, we can just go, let's take the full BGP table and pick some random prefixes. But as I said before, that's not very useful. If you look at NetFlow, you'll find that most of the traffic is coming from pretty much local destinations, local to your upstream provider or their upstreams. Well, let's think about it this way. I've taken the picture, AS110, 130, 140, which we saw earlier, and I've added a piece to it. So if you're AS110 here, you announce your address space to AS130. AS130 announces your address space to the customers. Where do you think traffic from, say, customer 5 to you will go? Well, it's going to go from customer 5 to AS130 to here, isn't it? It's not going to go customer 5, AS130, transit, internet, AS140 to there. Much longer path. So if you announce your address block to your upstream provider, their customers are going to send their traffic to you through your upstream. So don't you think it makes sense to send the traffic from your upstream's customers via your upstream? It doesn't make much sense to send traffic to customer 5, 110, 140, internet, transit down this way, does it? Right? It doesn't make much sense to do that. No, you want the traffic to go in the direct path. You want traffic to go this way, traffic to go that way. Keep it as symmetric as possible. So that's what we want to achieve. Now we know how to get load balanced traffic into the network. But outbound, what we want to do is we want to accept AS130 prefixes and the customer prefixes in here. So full BGP table coming in from both providers. The full BGP table here will look for 130 and 130's customers and make them important. Push up the local preference. Right? So everything we learn from 130, high local preference. Everything else that comes from transit and the rest of the internet that comes through 130, low local preference. Okay? And that means traffic from 110 to 130 and the customers all goes this way. Traffic to 140 will all go that way, just using defaults. Traffic to the internet, yeah, we'll go this way. Some might go that way, who knows. But that way, we at least get local traffic to 130 and their upstreams going over these links, and 140 and their customers going over that link. So let's look at the configuration. So router C, we're getting the full BGP table. That still means we need a filter. Right, there's still prefixes in v4, and same for v6, which should not appear on the internet. So let's set up a prefix list. I've called it RFC 1918 deny, but it's more than that. There's certain special use addresses that should not appear in the public internet. You can look them up here. Team Cymru have a list, both v4 and v6. So look up what the list should be. I forget the RFC. I've written it down somewhere in the slide set. But there's an RFC that lists the special use addresses. Some of them should not appear on the internet. Okay, so that's the router C configuration. So we've got filter in. Outbound, we send our address block. And then we've got a route map I've called AS130 load share. It's not a built-in Cisco command. It's actually a route map that we set up. And the route map that we do is what I just described. What we're doing is we're looking for the prefixes coming in from 130. We're looking for those, and we're saying the prefixes originated by 130 and 130's neighbors, we're going to set a high local pref. Everything else, we're going to set a low local pref. That's what this is doing. So if it matches here, high local pref. If it doesn't match, we're doing this one. So we take the 460,000 prefixes from router C, from the upstream, it is router C, from the upstream, everything that's from the upstream and the upstream's neighboring AS, local pref 120. Everything else, local pref 80. Okay. Router D is boring, full BGP table in, address block outbound. Okay. So that's how we do it with the full BGP table. Router C, accept full routes from 130, tag prefix originate by 130 and 130's neighbors with local pref 120. Traffic to those ASs will go over the 130 link. If you find there's not enough traffic or it's still not symmetric, you might want to allow 130's neighbors in as well. It just depends. You know, this is not a one-size-fits-all. It entirely depends who you connect to. But this gives you the idea of what you need to try and do. And it gets you symmetric routes. That's important, symmetric routing. Customers complain bitterly if outbound packets go one way and inbound comes halfway around the world. So let's try and make it as symmetric as possible. So this is a strategy. Okay. Remaining prefixes tag local pref 80, Traffic to all other ASs will go over 140 link. Easy. But let's look at it, full table. Summary of the routes received. So AS140 gives us 460,000 at local pref 100. AS130 gives us this doesn't add up. Anyway, this should be 430,000. Let me fix it. I was looking at that earlier when I was doing the slides thinking, something doesn't look right there, but I don't know what it was. Oops. Don't know what it was. That's better. Right. Okay. 460,000 from 140, local pref 100. We'll just leave it alone. AS130, say we're getting 30,000 from 130 and 130's neighbors. I've made it up. You know, it seems reasonable if you go to like a tier 1. We're looking at them, making them high local pref 120. The rest of them, we're marking local pref 80. Grand total, 920,000 paths. And that's okay, you know, it's all fine, it'll work. If the link to AS140 goes down, the routers in your backbone then spend all the time stripping out 460,000 paths. How long does that take? Well, it doesn't happen in a microsecond. Depends on your router platform, it's anything from 2 to 20 minutes. And that's 2 to 20 minutes of instability for your customers because you'll have traffic bouncing between the two border routers. Because the link is gone, it'll probably bounce back and forth between the two border routers for a few minutes. Oh, there'll be that at least, yes. Yeah, there'll be big issues. This is actually quite slow to converge because of the sheer numbers. I think, if you were listening to me the other day when I was talking about the routing table report and the deaggregation that's going on, this is why I get a little bit cranky about all the size of the BGP table. There are only 190,000 prefixes that are useful. The rest are junk. And this is why, if we didn't have the rest here, we'd be speeding the convergence in multi-homing situations like this. Now, the guys at the core of the internet have less issues. They've got the biggest platforms with all the different tweaks and tricks to make this converge really, really quickly. But it still takes time. But the folks at the edge of the internet with the smaller routers, this is really, really painful for them. They're talking outages 5-10 minutes simply to converge if one link fails because they're carrying the full BGP table. Let's do it with partial routes. And what you do, ask one upstream for a default, ask the other upstream for a full BGP table. You can't go to your upstream provider and say, can you give me a bit of this and a bit of that and a bit of nothing else? You're not going to do that. It's either default or everything. So what you do, ask one for default, ask the other one for everything. And you're going to take the everything and throw most of it away. I know it sounds wasteful and all the rest, and you think, wow, we get 460,000 prefixes coming in and I throw away 430,000. But okay, once it's done it takes 10-15 minutes to do it all, but once it's done, it's stable. Here's how we do it. So router C, this is the one we're going to ask for the full BGP table. Again, with this filter, throw away the private address space, all the address space that shouldn't be routed. Outbound, we send our aggregate, filter list 10 in, route map tag default low. So they're going to give us the full BGP table, which of course includes the default. Let's look at it. Well, here's the AS path filter. It's the same one, but rather than doing a high local pref for these are the only prefixes we're going to accept now. So that's why it's applied directly to the neighbor. It's an AS path filter. We're only going to accept the prefixes originated by 130 and by 130's neighbors. Tag default low, we're going to look for the default route, local pref 80, make it the backup. So what are we accepting from AS130? Just the 30,000 prefixes that they and their neighbors originate, and the default route. We've used the default route to replace the entire BGP table. The whole BGP table has now been dumped. Okay. Now, let's go to the other one, router D. We simply get the default route, and outbound we send our address block, and that's it. So Router C, accept full routes from 130, throw most of it away. Only keep 130 and 130's neighbors. Allow the default in, set to local pref 80. Traffic to those ASs will go over the 130 link. Traffic to all other ASs will go over the 140 link. Guess what? This is exactly the same text as we had previously. It's the same end result as we had previously. Identical. All we've done is we said, full BGP table can be replaced by a default route. And so this is great if you're at the edge of the internet. You no longer need the full BGP table. You simply rely on defaults. Right. And what's the difference? Well, AS140, okay, these numbers are wrong. I suppose I should push save, just in case PowerPoint does its mega crash again. Okay, so that's what we have. So from 140, we get just the default. From 130, well, again, we get the 30,000 prefixes coming in through the AS path filter. But now we get the rest replaced by a default. Grand total 30,002 paths. How long does this take to converge if a link fails? Well, if the AS140 link goes down, it takes a microsecond. You literally don't know. It's just the default flips over. If the AS130 link fails, stripping out 30,000 prefixes, few seconds. Yeah, 10, 15 seconds, depends on your BGP timer. I don't know, I've lost count of the number of providers I've helped move over from this scenario to that scenario. And they all say, it's brilliant, you know, if a link goes down, they've got unstable satellite links, unstable long-haul links, fiber gets stolen, all this type of thing. Boom, 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 you know, the failovers like that. They really don't see it. And certainly with playing with the BGP timers and so forth, you know, the outage is literally a few seconds. And that's really the situation you want to try and be able to get into. I mean, what's the disadvantage here? I mean, if you never needed the full BGP table, you know, what did it give you? It didn't give you anything. You've replaced it with a default route. Of course, if you have customers who are multi-homing onto your network and they need full BGP table for their multi-homing, that's a decision you have to make. You know, if you end up getting customers who want full BGP, then it's going to cost you a network infrastructure. You need routers that have the tweaks and so on that lets you handle this very quickly. Because once you start carrying this, you're sacrificing that. You know, the quick failovers that you had before. Okay, so that's how to do multi-homing. Rather than carrying the full BGP table, we just have partial. If you want to inject, well, do nearest exit and so forth, you can inject the default route into OSPF. I've given some examples here. The default information originate. So C would be the backup, D would be the primary. So you can originate the default route by OSPF with different metrics. Lowest metric wins, of course. If you can't get default route from your upstream provider, then put a static default route to the physical interface going to your upstream. This puts it in the rib, then OSPF will announce the default through the backbone. So that's pretty straightforward. We'll jump over this. So partial routes from upstreams, not expensive. You only carry the routes you need for load sharing. You need to filter on AS paths, not exactly hard. And of course, you know, if you don't get enough traffic on one link, let some more prefixes in. Or if it doesn't seem to be symmetric to particular destinations, let those ASs in. You have to do a bit of research, but that's where NetFlow will let you see, you know, which destination you're reaching through which border router. Right? So there you can be selective. So the AS path I showed you, the filter I showed you, is an example to start with. Obviously, you'll have to add, but I can't give you an example that will work for you because I don't know who you connect to. And it entirely depends on who you're going to connect to. And again, when distributing default by IBGP, OSPF, or ISIs, make sure that peering routers have a null route for the default. This is really important so people don't use you for outbound transit. The reason I'm very strong about this is I've been bitten by it. I've seen many providers bitten by this as well. Make sure your peering router doesn't carry default or full BGP table or any destinations you don't want your peers to get at. Okay, I think I'm going to have time to do this one. This is a real live worked example I did a few years ago, and this was the solution that we came up with. We tried everything, and I think this will show you why having 3 upstream providers is just adding complexity. So how somebody with 15 upstreams managed to do any traffic engineering has been totally beyond me. I mean, I saw the configuration, and I can't see how any customers could have been happy, but anyway. So here we go. This was the example. It was all real bandwidths and everything. 3 upstream, 16 meg, 8 meg, 4 meg. What is the strategy? Well, we can get 3 times the full table. 3 times the full table, 1.3 million paths. Yeah, that's all right. You know, Cisco, Juniper, all the rest. We happily sell you 2 gigs of RAM. Other option was partial table and defaults from each of the upstreams. Well, you know, the full table solution was the same as before. You have to start filtering AS paths and doing local prefs and all this type of thing. But, you know, we didn't have routers that could carry full BGP table. Well, we could, but not at this level. And handing 3 upstreams to handing 3 full BGP feeds, we were talking outages of 10 minutes or so if any link failed. And given some of these, well, one of these links, actually no, this time all these links were satellite. And, you know, with satellite and fog and rain and falling out of sky and all this type of thing, solar flares, you know, there were a lot of outages on these satellite links. Or when the upstream provider needed, I need to sell the bandwidth to the government. So, sorry, you're not going to get your 16 meg. We'll just take it away from you for a couple of hours. It's like, what's going on? Anyway, so here we go. Notice what I've done. The link to ISPA 16 meg I've put on one router. The 8 and the 4 meg links I've put on the other router. The theory being if this router fails, I've still got 12 meg of bandwidth. Or if this one fails, I've still got 16 meg of bandwidth. It seems to be a sensible separation to try and split it in 2. Notice 2 routers. Don't need 3. There's no need to have a 3rd router here at all. And they were coming into the same physical location. So this was fine to do. 2 routers is all you really need. Available feeds from the upstream, full table, iBGP and the default, and default route. This one was bizarre. I have no idea how that could have been useful at all, but that's what they offered. So we elected default route and full table. We took the default route from the biggest provider, biggest connectivity provider. So the one that was 16 meg link, we took the default route. The reason is that the other 2 paths, I'm going to take all the prefixes but throw most of them away. Other 2 paths, I'm only going to take them and their neighbors, nothing else. So if I took the default route from the smallest one, I'll be keeping most of the prefixes coming in from the biggest connectivity, so I get more traffic going out that link. Right, so we get the full table from B and C and throw most of it away. But how do we decide what to keep and what to throw away from B and C? Most traffic is going to use the ISPA link, so we need to find a useful subnet. So the way we ended up having to do it was, right, what we'll do is we'll look for the prefixes transiting the 9 tier 1s. 9, 10, I don't know, something like that. But at the time it was 9 tier 1s. Because, well, you know, if they go, that's the bulk of the internet. And given the biggest link was to ISPA, that's going to be bulk of the traffic, in theory. And also we're going to throw away prefixes with ISPA's AS in the path. If we go to ISPB and we see ISPA coming in through there, well, what's the point? Because we've got a direct link to them anyway. So it didn't make any sense to accept those prefixes. So the AS, these are the tier 1s. So AS 209, 701, 1239, 1668, 2914, 3549, 3356, 3561, and 7018. So we set up an AS path filter. So that's the one I showed you before, but added a lot to it. Anything that goes through a global tier 1, we dumped. Okay, because we're going to hear that through ISPA. This is the ISPB link. So we're going to hear these through ISPA anyway, through the default. So we don't need these locally. We're not going to hear ISPA because we've got a direct connection to them. We're not going to hear C because we have a direct connection to them. So what are we left with? Well, we're left with ISP-B, anything they originate, their customers, the customer's customers, the customers, and so on. You can make this access list as big as you want, or as small as you want, just to make sure you get symmetric routing. Now, in this case, the satellite links, where did they go? I'm trying to remember where they went. I think it was London, Hawaii, and Japan. So it's not like they're going to the same place. So symmetric routing was really important. Really, really important that it was symmetric. Because if they weren't symmetric, you would end up with really, really big round trip times. So we look for ISP-B and their neighbors, the neighbors, neighbors, and neighbors, neighbors, neighbors. Even if these guys connected to a tier 1, we wouldn't get the tier 1 in the path because it would be caught somewhere in here. So this actually worked amazingly well. We dropped the global transit ISPs, we dropped prefixes transiting A and C, permit prefix from B, their neighbors, 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 and so on and so forth. The more AS path clauses, the more outbound traffic. And what we did was, each one we added, we checked that the routing was symmetric. We made sure that that the traffic coming in and out was symmetric. You look at net flow, right? You send a packet out to a destination, does it come back in that path? Net flow will tell you. Nothing else will. And once it stopped coming in that path and went some other way, then we didn't do the prepend. So this was pretty useful. We did the same thing for ISPC peering, pretty much the same thing, same type of AS path filter and so on. So the largest outbound link should announce just the aggregate for outbound. What about the other links? Aggregate with AS path prepend. That's what we started with because we wanted it to be symmetric. If you have a situation where the destinations are in the same geographic location, then you can start subdividing prefixes of the aggregate as well. All that we needed to do was just announce the aggregate with an AS path prepend. That was enough. And it was amazing how well this worked, given we're going to 3 different parts of the world. All right, so here's a configuration example. For the biggest provider, default in, aggregate out. Simple. For the B provider, right, prefix list, ISP-B out, route map to B out. Inbound, we had the AS path filter I showed you earlier. ISP-C, same thing. And here we go. So here's this is just an example. We send the aggregate out. It may be your dial-up network customers you send this way. And maybe your business customers you send that way. We do a single prepend for the aggregate towards B, dual prepend towards C. These are all the variables that, as you can see from this, there's so many things that we can adjust here. I mean, I've probably made it more complicated than it needs to be, but I've literally cut and pasted the configuration and changed the addresses of what we ended up doing. Because they had a dial-up network. I mean, it's now a broadband network. And the problem we always had was that the broadband customers were really cheap, didn't pay very much. And so, wow, they could go and buy a rate limiter box. But we thought, well, we just push all the dial-up customers over one of the satellite links. And once the link's full, too bad. They were paying nothing compared with what the business customers were paying. These guys were paying big bucks. So we made sure that they got the best connectivity possible. And they couldn't be swamped by the dial-up. And we didn't need any rate limiter boxes. Right, so that's the sort of example we did. Right, so got a default route from ISP-A by eBGP, mostly discarded full table from B and C. So again, this is just how to inject it in with OSPF. I'm going to jump over this because it's a case of the upstreams didn't give you, well, sorry, no. It's a case of you don't want to rely on BGP for your exit. You want to rely on OSPF. Don't distribute a default route by iBGP because iBGP gives you the best path over the whole backbone. And it will just be one exit point. OSPF, it's biometric to the exit. So you distribute the default route by OSPF through the backbone to do the nearest exit. So this is just showing you, telling you how to do it. So I'll jump over this. Right. Okay. So router A configuration, what was this? Oh yeah, this is the iBGP configuration. So in the border routers, don't propagate the default route. Okay? Don't propagate the default route. So here's an example. I've used a BGP filter that says deny the default route, allow everything else. You could also use a BGP community, the no advertise BGP community. When the default comes in, tag it no advertise, done. Then it's not announced anywhere else at all. Right, so this is typically what you put in your border upstream router, so the default route doesn't get propagated on your backbone. Do it by OSPF or ISIS, whatever you're using. So this example is based on many deployed working multi-homing load balancing topologies. 3 upstream providers with unequal bandwidths. You can see it's not straightforward. But we've done it with not using the full BGP table. No 1.38 million paths. We've done it probably about 40,000 paths. Much, much easier. It's light on the border router resources, light on the backbone infrastructure, and so forth. So this has been pretty good. So the final piece is all about communities for traffic engineering. So I've shown you pretty much all there is to do with multi-homing. The real world is all of what I've talked about up to now. It's just more complicated. So if you can get a grasp on what I've talked about so far, your own multi-homing scenarios will all be based on this. You'll just have your own circumstances to deal with, your own connectivity to deal with. But these are the principles you want to follow. Communities are the final piece of the puzzle. Communities are so incredibly important for doing proper traffic engineering. And as I said at the start, if your upstream provider is not supporting communities, it makes your life really difficult. Most of the operators that I've worked with recently, the chief engineers have pretty much said to me, if the upstream won't handle BGP communities, I'm not buying service. It's really come down to that. Because an upstream that supports communities, which I'll show you, makes it very easy for a customer to do their own traffic engineering. And, the end users are so fussy these days. They want everything to be perfect. So if you can't control your traffic engineering, then you can't deliver service to your customers and they go elsewhere. Right, it's a very powerful attribute for assisting and scaling BGP multi-homing. So most ISPs make use of them for internal policies. That's pretty common. Inter-provider relationships, so MED replacement, and customer traffic engineering. So I'll try and show you some of these. So the 4 scenarios, RFC 1998. Now, BGP communities defined in RFC 1997. 1998 was a simple informational RFC about how communities were used in one ISP's backbone. Even though it's informational, it's become the defining document for how ISPs use communities. It's quite interesting how it happened. It was always like almost back of the envelope type idea, put together to an IETF with some simple code that was given to Internet MCI, and bang, we now have BGP communities. People have taken the original concept and extended it. We're going to look at how it's used in the backbones and is used for policy control as well. So informational, RFC 1998, how to implement load sharing and backup on multiple inter-AS links. The idea really was to give control to the customers. And also, it simplified the upstream provider's configuration. So these are the values here. We had, well, this number here, the convention for the community is a 32-bit integer, but the internet convention is the first 16 bits are your AS number. And the final 16 bits, you pick. Choose what you want to do. Of course, an aside, ISPs with 32-bit AS numbers go, oh, what do I do? This is 16 bits, I can't put my AS number in here. This is not an AS number. It's just a 16-bit integer. As you find in the examples I'll show you, a lot of providers just use private ASs. It's just an indicator. But the convention is put your own AS number in there. So if you've got a 32-bit AS number and you want to use communities, just use one of the private ones, 64512 up to 65535, or 65534. So just use those. Or just use 1234, it doesn't matter. It's just a number. Anyway, so this one, whatever number here, colon 100 means set local pref 100. The router doesn't do it automatically. You've got to do a configuration. I'll show you. But this is what they mean. :90 set local pref 90. :80 set local pref 80. That's if you're dual homed on the AS and this path is the backup. Remember I set local pref 80 in the dual homed example about 100 slides ago? :70, main link is to another ISP with the same AS path length. Sorry, this is 80. 90 is the backup. And 70, main link is to another ISP. That's how it was used for signaling. Okay? Upstream ISP defines the communities mentioned. The customers then attach the communities they want to the prefix announcements. So, for example, if to declare a particular path as backup, customer would announce their prefix with community 100:70. AS100 would receive the prefix. It would see this community and go, I need to set up a route map that sets local pref to be 70. Configuration, here. Customer router has this route map, AS100 out, send community, which you need on Cisco's, and then route map AS100 out, match AS path 120, so any prefix originated by me, we set community 100:70. Okay? And then out it goes to the upstream provider. Upstream provider has this configuration, has a route map customer policy in. The route map is defined on the next screen. So let's define some communities first. Well, here's the 100:70 I mentioned. Here's the 180, here's the 190. Now let's look at the route map. And this route map, so in comes the prefix. It looks for the prefix and the community that's set on it. If the community is what's defined in list number 7, which was 100:70, we set local pref 70. If it's 180, we set local pref 80. 190, we set local pref 90. If there's nothing set at all, we set local pref 100, which is the default. Okay, so that's pretty much RFC 1998. So if the customer changes from 170 to 180, the local pref changes. So the customer can change the load balancing without the upstream ISP having to do anything at all. Now, yes, you could do this with MED as well, but remember we're talking back to the days when MED was broken. Right? So Wellfleet's idea of a MED was, well, infinity if there was no MED set. Cisco's idea of no MED set was that it was 0. And so interoperating between those vendors was, well, with MEDs, well, you couldn't to get a predictable result. So ISPs started using communities for this type of signaling instead. And this is why, even though this is more configuration, you've got so many other options available with communities, as I'll show you later. This is now the preferred way of managing policy between customers and ISPs. So it was very inspiring. There are no standard communities. Best practice today is that ISPs should use communities extensively for multi-homing support and traffic engineering. Most ISPs will document what the community policy is in the route object, in the AS object in the Internet Routing Registry. Or if it's not in the Internet Routing Registry, they put it on their website. You can usually find on the BGP pages what the official policy or community policy is. And I'll show you some in a bit. All right, so 1998 was fine for simple situations. ISPs create backbone support for many other communities to simplify and give customers more control. We had the well-known communities, of course, but these were like no export, no advertise, the Confederation one, and what was the other one? Anyway, those standard communities, or for no peer as well. You know, but there's no official public standard for what the communities should be. I mean, there was documentation a long time ago. At MENOG 40 presentation, there was a list of some of the communities that operators were commonly using. And I've actually documented some of these in the next slide. But they usually publish them on the website or the AS object. But here are the common ones that are used. Right? You remember this one from RFC 1998. Number 80, means set local pref 80. But ISPs have done the reverse as well. 120, set local pref 120. Make it more preferred than the default. Okay? Here, three interesting ones. If you send whatever :1, set AS path prepend 1, AS path prepend 2, AS path prepend 3. This one's interesting. Well, 666. This is useful for dealing with DOS attack mitigation. I mean, providers have different ones, like level 3 is 9999, 666. China, it's 444, because 4 is the unlucky number in Chinese. 666 means the devil in the US, apparently. 999 is, well, it's the UK emergency number with an extra 9. But anyway, you've got some community like that that's used for remote trigger black hole filtering. This one is interesting. Do you know remote trigger black hole filtering? Yes? No? Yeah. Yeah. What you do is, if you've got an address that's under attack, what you can do is you can announce this address to your upstream provider with that community if this is what they support for remote trigger. And what they will do is they set the next hop for that destination to 192.0.2.1, and they have a static route to the null interface for 192.0.2.1 on all the backbone routers. So all the traffic coming in, it sees the best path to this attacked address to this next hop rather than the normal next hop, and everything is dropped in the null interface. So that's remote trigger. The remote trigger is you sending the announcement with that community, and black hole filtering is null routing the traffic. Okay. So that's what that's about. I mean, again, it was mentioned in the presentation on, I think it was Sunday, wasn't it? Sunday afternoon. So again, if your upstream provider does this, good upstream provider. If your upstream provider can't do this, start talking money. I mean, frankly, these days, there's so much stuff happening on the network, your upstream has to be able to support RTBF. Honestly, they really do. Anyway, but these are the typical BGP communities that you find most upstream providers will support. I mean, the number here varies, as I was saying earlier, but 80, 120, 123 are very common. Very, very common. I mean, don't just assume your upstream supports these communities and start sending them. Talk to them first. See what they support. They may support them but not publish anything. Or when you send them an email, they say, hey, do you support BGP communities? Classic one I got a few weeks ago is like, oh, we don't use BGP communities. They're too complicated and they don't serve our purpose. I'm like, okay, well, whatever. I mean, it's industry best practice pretty much. But let's look at the configurations. Where would all this go? I've kind of collapsed all this into one router. So we've defined a community list here. So here we go, 1 prepend, 2, 3, 80 local pref, 120 local pref, the black hole route. I've set up a static route to null for the 192.0.2.1 destination. The null interface on most mainstream routers is special. It means drop packets. There's no processing that happens at all. You can do gigabits per second to the null interface, the packets just disappear. It takes no CPU to do at all. So this is a good thing to do. And then we've got two route maps, and I've got them on the next slide. So this is the connection to the customer. So we do customer policy in. This is the connection to the upstream provider. We do the upstream out. So let's look at these two route maps. So coming in from the customer, if they send community 4, what was that again? Community 4. Ah, right. Local pref 80. If they send community 5, which was whatever colon 120, local pref 120. If they send us community list number 6, then, oh, they wanted us to do a black hole of this particular route. Send 192.0, redirect it to 192.0.2.1. And there may be others as well. Some of the big providers have got, this goes on for pages and pages and pages. All right. What about towards the upstream? Well, this is if the customer sends something that says, oh, do a prepend towards the upstream provider. Single prepend, there we go. Double prepend, triple prepend, and there may be others as well. Right, so they appear in two places. So the customer may want to use you for your primary path, and maybe your customers for the primary path, but they don't want to use your upstream provider. So you can give them the option, and they can do 1, 2, 3 times prepend up to whatever they want to do. You're probably thinking, wow, that was really going to mess with my multi-homing. Well, yes, it is, but you've got to weigh up the pros and the cons. Happy customer who can break his BGP and then you can send professional services in to help them? Or unhappy customer who can't do anything or phones you every 5 minutes when things don't work properly? I prefer not to speak to customers. What do I say? You know, good engineer, lazy engineer. Get all this stuff set up. That's the good engineer, then you can be lazy afterwards because the network and the customer look after themselves. So here's some examples. You cannot read this, I'm sorry. But this is what Sprint do. They're one of the global tier ones. The webcast folks definitely can't see this, but it's hard to see even in the room. But look, they don't use their AS. There's no 1239 appearing here. They're using the private ASs. This is 65,000. So 65,000 XXX. Well, this XXX is a list of autonomous systems that they peer with. And this says 65,000 XXX, customer sends this, do not advertise to AS XXX. So they can do single prepend, double, triple, quadruple, and so on prepends towards whichever AS you choose. Pretty nice, isn't it? Do not advertise, this one's in Asia, this one's in Europe, the list goes on. You can go to this URL and you'll find Sprint's complete list about the BGP policies. That's pretty nice. You know, they've got a good community policy set which customers can do stuff with. So say if you're connecting to APIA 3356, then you can announce your prefix to Sprint with, I don't know, maybe a 3 times prepend with this community 65003:3356 and it'll do 3 times prepend towards 3356. You know, I've worked with lots of ISPs who've connected to upstreams with this type of policy, and the communities are very effective. They really do work well. Here's Verizon Business Europe. Well, guess what? There's the 80, there's the 120, here's the 123. They've got these 2 extra ones as well. That's keep within Europe. This is for customers. And they've got some other ones as well that they've added in. But again, this is in the AS object. You can look it up. whois.ripe.net for AS 702, and you get this, amongst lots of other things. This is BT in Europe, BT Ignite, AS 5400. Very complicated one, but they've got the same idea. If you send 5400:1000, they will not announce this prefix to all the peers or transits. If you send 5400:2000, they'll do a single prepend towards peers and transits. And then you've got, well, for example, towards SAVIS, 5400:1502. If you send that, it won't announce the prefix to SAVIS. Or it'll do a single prepend towards SAVIS, and so on and so on. So that's BT Ignite's one. Level 3, there's the black hole. If you send 3356:9999, it will black hole or discard the traffic towards the prefix with that community attached to it. Okay. Otherwise, you know, they've got set local pref 70, 80, 90. They can do the prepend thing, and there are many, many more in their list as well. What about NTT? This is AS2914, another tier 1. Their default local pref is 120, but you can change local prefs according to this list here. You can do the prepends 1, 2, 3 times towards customers, BGP customers. You can do prepends towards NTT peers, like this. And so on and so on and so on and so on. Very big list as well. Okay? Right, so these tier 1s cannot live without this community support. I mean, what was it? It was something, I think it was VJ Gill, when he was at America Online, was talking about how much a support call that came into AOL's global backbone cost them so much per minute to deal with. And if they could get the BGP customers not to have to call the support center, then it would actually save money and be able to do more things. I think it was VJ was talking about this. It was some incredible cost analysis that he did. And so doing the effort of setting up stuff like this bought them a lot of help desk minutes. They didn't have to work with customers to sort out traffic engineering problems because customers could go and do it for themselves. So this is worthwhile thinking about. Consider creating communities to give policy control to your customers. Reduces tech support burden, reduces the amount of router reconfiguration because you've got a standard configuration on the router. You can use a lot of these examples if you want. I mean, I've done some examples here as well, just to show you how you might want to try and do something. ISP have a choice how to handle policy for customers. You can do no delegation at all, don't give the customer choice, but then you've got cranky customer because they can't do the load balancing properly. Or they have to phone you up or send you email, and they've got to open a ticket, and it takes 24 hours to get answered, and their customers get cranky and so on. Do you want to do that? Or do you want happy customers? Give them some delegation policy. The tech support doesn't need to be involved. And if you don't want the tech support to be involved, BGP communities are the way of signaling all this. So here, this is what we're going to play with. This is just a worked example for you. I set this up for an ISP in Asia, actually. It's pretty much, this is what I did for them, and all I've changed is the numbers to protect them. But, you know, if there's no community set, just announce it everywhere. Standard announcement. If the customer sends whatever :1, single prepend, double prepend. These are the standard ones: 80 backup, 120 primary. 666, black hole this route, please. 5000, don't announce to any BGP neighbor at all. And then we came up with this scheme: 5AA, don't announce to BGP neighbor AA. 5AAB, prepend B times to BGP neighbor AA. Right, so the customers have got lots of what they can do. And so, you know, on the web page, we have a list of what the BGP neighbors are, and so they can do 1, 2, 3 times prepend. Right, so the BGP configuration for initial communities was discussed somewhere, yeah, a bit earlier. But we've got new communities we're going to look at in a bit more detail. So if a customer tags a prefix announcement with 100:50:30, it means don't send prefix, so the 0, don't send, prefix to BGP neighbor number 3. So on your web page, you define BGP neighbor number 1 is them, 2 is them, 3 is them, and so forth. 5102, 2 times prepend to neighbor 10. Let's define some communities. Right, so here we go, 5000, don't announce anywhere at all. Single prepend to all, 2 prepend, 3 prepend to all. Don't announce to peer 1, 1 prepend, 2, 3 prepend to peer 1. Don't announce to 2, 1, 2, 3 prepend to number 2. So we define all these community list definitions like that.
So this community list should be famous, okay, with all ISPs, right?
No, this community list, this is for you as the backbone provider.
These numbers of the one.
Yeah. So that means this is your AS, for example.
Yeah.
Yeah. But this is for you, right?
Oh, okay.
So what you do is you publish this list for your customers and say, dear Mr. Customer, if you don't want to announce your prefix to peer number 1, send me this prefix. Sorry, send me this community on the prefix.
This is an agreement between me and the customer.
Well, it's not even an agreement.
No.
You decide.
Yeah.
You tell the customer. But yeah, I mean, it's agreement, whatever. Yeah, but you make the decision. This is what you're going to do. Right? So here we've got it for 2 peers, and this one means don't announce at all, or do the 1, 2, 3 times prepends. So you decide what they are. I mean, the list was actually a lot longer because this provider had, I don't know, what was it? 5 BGP peers, I think it was. There were 2 upstreams and 3, 4, no, yeah, 2 upstreams, 5 peers. So it was quite long. But, you know, they gave the customers the option, if they don't want to send traffic through this transit provider to a peer, and because they want to send it another way, there they go. They can do it. And so we implement it. You know, again, the route map. Sorry, it looks a bit complicated, but, you know, route map for BGP neighbor number 1, match IP community 100.110, which means the deny means we're not going to announce these prefixes. So community 100.110, what were they? Well, 100 is here, don't announce anywhere. 110, don't announce to peer 1. Right. So this is a route map that goes to BGP peer number 1. The step number 20, but we're going to do a single prepend. Right, so 101 means single prepend to all neighbors. 111 is single prepend to neighbor 1. 2 prepend to all neighbors, 2 prepend to neighbor number 1. So 100, 101, 102, 103 applies to all BGP neighbors, whereas these ones apply to the specific neighbors. Okay, and then we do the 1 prepend, 2 prepend, 3 prepend, everything else gets left alone. So once you think through the steps, it becomes quite straightforward to do. BGP neighbor number 2, just to give you the idea. So rather than 110 here, we now have 120, 121, 122, 123. Same thing. Neighbor 3, neighbor 4, neighbor 5. Same thing. And so for the ISP, right, so here we talk to BGP neighbor number 1, route map out. We have a policy in, whatever that is. Neighbor 300, this is BGP neighbor 02, route map out. So when the prefixes with the right communities hit this router, they get run through the route map, and we do the right prepends and filtering and all the rest. Okay, so it's actually, when you see it summarized like that, it becomes quite simple. I mean, of course, you're not going to call the route maps this. You're going to call them what the actual ISP neighbor is called. Make it a nice, friendly configuration. And okay, this one is where it connects towards the upstream. So the route map towards the upstream. Right, sorry, yeah, this is the customer configuration. So if a customer is sending the address space towards the upstream provider, here they're setting particular communities. So 5010 and 523. So this says, don't announce a prefix to peer number 1, 3 times prepend to peer number 2. Right? So he's setting the 2 communities and on this particular address block. And then otherwise he's sending the aggregate outbound. So to do a 3 times prepend of block A towards the upstream second BGP neighbor, don't announce block A towards the first BGP neighbor. Now, can you imagine picking up the telephone and telling technical support of your upstream provider, oh, yeah, can you do a 3 times prepend to them? You're not going to a fast food restaurant. But that's what it ends up being. Trying to deal with a big provider with multiple exits, it's not like, do you want chips with that or anything? You want to be able to do it yourself. And there you can do it yourself. You as the customer can just set your communities and you can pick the transit load balancing that you require. And this is why there's so many operators, the mid-size operators, the regional providers, are demanding of their upstreams, please give us communities. I don't want to sit on the phone for 5 hours explaining to your help desk all the different communities I've got to try and deal with, all the different load balancing I need. I would rather sit on my router doing set community and figure it out based on what's provided there. And this is so simple. Once it's in place, this is so simple to manage. You can give your customer a configuration like this. This is a template. And say, look, whatever sub-prefix you want to do this prepending or not announcing, put it in here. Pick the communities you need. Make sure your aggregate goes out. Customers love it. They can tweak all these things. And I've seen some of them. You know, some of the little ISPs I've helped in South Asia gone, oh yeah, this is really good, and they try this, and hey Philip, you see what happens when I do this? I cut myself off from Europe or whatever else. You know, they like playing with this thing. They no longer have to talk to their upstream. Usually it's a long phone call, big time zone changes, help desk who's got 10,000 customers and they can't tell the difference. Right? Your 10,000 customers, it's like, yeah, a long list. Whereas for you, you're utterly important for yourself and your customers rely on you. It's much better being able to do this. But notice how much control the customer now has. Customer flexibility, tech support doesn't need to be involved in the upstream. Yes, the disadvantages, and this is the excuse I hear from the biggest providers, customer could upset my load balancing. Well, yes, but don't you want a happy customer? You know, it's one or two who refuse to do communities that keep saying this. But the advantage is this, you don't need such a big tech support dealing with issues. All right, communities are fun, extremely powerful tools, so please do think about community policies. I've hoped that what I've given here will give you a bit of confidence if you're not playing with communities already, to go and try some. I say a lot of the biggest providers are using them extensively, can't imagine the world without them. I mean, I've been doing them since '96 when they first appeared in Cisco iOS, and honestly, they're such a major lifesaver for a lot of multi-homing situations. Anyway, multi-homing, not hard. keep it simple and stupid. Full routing tables rarely required. And here's something to think about. If customers want 460,000 prefixes, charge them money. Make it expensive for them to get the full BGP table. Because you have to add the extra infrastructure, it has the impact on your routers and all the rest. So why not? Anyway, sorry I've overran by 5 minutes, but that's the end of the tutorial. Hope it was interesting. I'm happy to take questions on email or whatever else. The slides, if they're not on the MENOG website, they'll be there as quickly as I can put them up. Otherwise, enjoy lunch. I'll be back here at 2 o'clock. So lunch is in the restaurant downstairs, right under where we're at.
What's the link?
The link. Where's the link? Let me put the link up. Yeah, for those who weren't here right at the start, here's the link. So I think I've put them on my repository here, and they will be on the MENOG 13 website at some point. But if you just go to FTP/seminars, look for the MENOG 13 files, they'll be there. I'm pretty sure I uploaded the tutorial.
I have a question.
Yes?
It's regarding the IXP.
Mm-hmm.
Okay, you have put a switch in place for the common router infrastructure.
Yeah.
So every provider has to peer with every other provider.
They don't have, okay. No, every provider doesn't have to. Providers will peer with who they want to peer, because you get two types of peering policy. You've got open, which means they'll peer with anybody. You have got selective, which means that let's have a conversation, maybe let's go and have dinner together, maybe let's look at the net flow stats, maybe if I like you. It can be down to, that's what selective means. And others have closed. And closed peering generally means that they have a list of ISPs that they'll peer with, and they will not peer with anybody else no matter what you do. So you tend to find those three different peering policies that ISPs have. All an exchange point is facilitating people to do that. I mean, I'm going to talk about a lot of this afternoon in the exchange point tutorial. But you have those three types of peering. So when you get an IX that has mandatory peering, it breaks that model. And those are the three types of peering that you get. An exchange point is literally an Ethernet switch where anybody can come and plug in. As long as they have an AS number and their own address space, then who they peer with is entirely up to them. And that's generally how they work. As I said at the start, the global peering forum, pretty important to have. There was the last MENOG, we had a MENOG peering forum as well. I mean, that was the same idea, to encourage ISPs to talk to each other so the peering coordinators get to know each other. Because you'll find exceptions, like selective peering policy, you've got to be nice to them. So if you send them an email, they go, nah, forget it. But if they know who you are, and you're a nice guy, and they're happy with your company, and it's all the rest, they'll probably peer with you, because they'll recognize the email. And you may even be able to get underneath the ISPs who have got closed policies. Because even though closed is only an official list, you can do the, oh, come on, you can be persistent, pester them. Look, look how much traffic, let's peer. And then they go, oh, yeah, okay, what the heck, So anyway, that explains it. You have those three. So no mandatory peering. It's all whoever wants to peer with whoever. And that's it. But I'll talk more about it this afternoon. So this afternoon here we have the exchange point tutorial, which talks about a lot of this stuff. Anyway, let's go and have lunch. Try and get back here for 2. All right. Thanks, everybody.